Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. In this video, we're going to be looking at propositional logic. In particular, we'll be covering truth functions and the definitions of the basic logical operators we introduced in 6.1, our last video. So welcome back, everyone. In this video, what we're going to be looking at is truth functions. And we're going to be overviewing the basic definitions for the bivalent definitions, rather, for the basic logical operators of negation, disjunction, conjunction, the conditional, and finally the biconditional. So actually we have a lot of interesting stuff to talk about today. But let's start off with a sort of quick review. We talked about, remember, let's start with the concept of validity. Remember, we said that an argument is valid if the premises are true, the conclusion necessarily must also be true, right? So we said an argument, if the premises are true, then the conclusion necessarily must be true. That's what a valid argument is. Now, why am I bringing this up? Because what this means is that valid arguments are truth functional. You might think of it like this, is that the truth can flow from the premises to the conclusion. So they're functional in that sense. Now, and what we're going to see today is that each of these logical operators funnels or truth flows differently through each of these logical operators, okay? And remember the concept of bivalence. Something is bivalence just refers to the idea that a statement is either true or false, not in between. In fact, this is sometimes referred to here as, well, in Aristotle, it's referred to as the law of the excluded middle. There's no middle ground between truth and falsity. Either a statement is true or a statement is false. Now, of course, when we say a proposition is either true or a proposition is either false, it has the bivalent properties, okay? So you're going to see that this is going to play a really pivotal role in our discussion today about how these logical operators affect the truth functionality or the truth flow of various arguments, okay? So what I want to do here, before we sort of get in here, let me make a couple other distinctions. We're going to introduce something today we call statement variables. And I was a little probably fast and loose with my terminology in the last video, okay? We talked about the idea that in propositional logic, when you have a basic proposition, for instance, I think we used the example, George is a clown, right? In propositional logic, the proposition becomes the atom, if you will, the basic unit, and it gets symbolized by a capital letter, right? In this case, the capital letter G. Now, statement variables are different because we're going to use, very much like algebra, we're going to use statement variables to identify some of the primary patterns of reasoning that we see. But because these statement variables can stand for anything, we're going to use lowercase letters. So these are going to be lowercase letters, for instance, and we're going to use the letters P, Q, R, and S, okay? Now, the reason this is going to be important is because we're going to use P, Q, and R, and S here as ways to, the P, the Q, the R, and S can stand for any particular proposition, any proposition in the universe. So they're purely formal. For instance, if you took algebra, you'll remember, for instance, they have G of X function, for instance. We write it differently, but right, if you remember in algebra, you have G of X function, where this stands for any sort of possible equation where G and X can be multiplied out or whatever, okay? And that's the same thing with these statement variables, because we're going to use the statement variables to really just construct universal forms of logical arguments. Whereas the capital letters here, right, these are always going to stand for particular propositions. Okay, so that means that we can use the statement variables to construct what we were going to call statement forms. Okay, statement form. So let me give you an example. Let's say we say, here I'm using the lowercase letters, if P, then Q, okay? This is, for instance, a statement form, and since I'm using a statement variable, it stands for any proposition in the universe that basically uses a conditional, right? So for instance, if I went up here, if I said, if George puts makeup on, then he is preparing his act, his clown act, right? So you can see here, this would be symbolized with a capital G, then M, right? If George puts makeup on, then, actually here, no, then he's preparing for his act, right? Now, but you can see here, this stands for the particular, but this can stand for any conditional statement form that ever exists in the universe, right? And one of the things that's going to be important, and the reason I want to mention this now is because as we continue through the course, some of you are going to have difficulty with this, right? Is that the P here can actually be a variable for a longer phrase, and so can the Q, right? So for instance, the P here could be, could actually stand for an R and an S and a T or a W, right, for instance. So for instance, imagine if I wrote this out. R and S, therefore T or W, right? Now notice here that this is a long phrase, but really I could just symbolize this as saying this is the P and this is the Q, therefore you have the P, therefore Q, okay? You can see that because these are variables, they can stand for much longer propositions, sort of like I think I gave the example last time of the Russian doll boxes, right, where the doll there's many dolls that sort of fit inside of each other. That's the same thing with these variables. So the statement form here can stand for really a lot of different things, and even very complicated arguments can be simplified by using these statement forms. And I'm explaining that now. You're going to, in our homework for this section, we're not going to really spend too much time where you have to deal with it. Well, maybe you will. But you'll see that later as the chapter continues in propositional logic, and especially when we get to natural deduction, understanding that a P, a lowercase p or a lowercase q here, can actually refer to something very complicated, right, will become actually pretty critical and important. So we can substitute the P for longer phrases, okay? The next thing we're going to sort of talk about here to introduce here is what's going to be known as a truth table. And in fact, you're going to see that in our next chapter, we're going to spend a lot more time talking about truth tables. But we're going to say that all a truth table is, oh, I don't know what's going on there. Oops, let's scroll down. All a truth table is, it is a way, let's say this, that the truth table is, what's wrong with my pen? The truth table is a means for symbolizing the bivalent properties of a statement. Sorry, my handwriting is not doing well today, which I apologize. I'm obviously a victim of the 21st century here. We're used to using computers, and my handwriting, especially on this tablet, is very difficult. Okay, now what does this mean? The truth table becomes a means for symbolizing the bivalent properties of a statement or proposition, okay? So let's take a basic statement. Let's go back to our George is a clown, right? And we'll symbolize by G. That proposition, George is a clown, has two possibilities. And what we're going to do is whenever we see a capital letter, or we can put it for a variable, because remember the G can also stand for the variable here, that means that it's either true that George is a clown or it's false that George is a clown, right? And the same thing goes with any P, even if the P is one of those Russian dolls, right? It means that P is either going to be true or P is either going to be false. Now, what we're going to do here is we're going to see that the logical operators function differently between different types of, between the different ones, between the different statement variables, okay? So let's sort of go through here, and what I want to do now is just go over the, let's see here, the definitions of the logical operators. Okay, so let's start like this. Let's say, and I'm going to do this, I'm going to say we have P and we have Q, right? And right now we're only going to start with, well, actually here, you know what? Whoa, pardon me. Oh, I'm having a rough morning, I guess. Okay, let's see here. Let's delete that. Okay, so let's start here with negation. Okay. Remember, negation, we use that tilde, okay? Now remember, the negation only works with one proposition or one variable, right? So let's just, since we're defining these, we're gonna be using the variables, since we're not gonna be looking at particular propositions at this point. Right? So if you have P, right? P can either be true or false, but what happens when you negate P, right? Well, basically, if P is true or false, if you negate P, it has the effect of reversing, reversing the truth, right? So if P was true, then if you negate it, P becomes false, right? And if P was false and you negate it, then P becomes true, okay? So what essentially happens here is negation means that you end up with the opposite truth value. Okay, so if P, right, if you have P, it just switches the opposite. It's pretty simple, okay? So let's go down here. We're just going to go through these. I'm going to go through these here as quick as I can, but hopefully in a way that makes sense for all of you. Okay, so let's look at conjunction. Okay, and now the first thing to remember conjunction is that dot. But remember, conjunction, unlike negation, needs two separate variables. So this is why we need a P and we need a Q, right? So let's sort of draw like this. And then these are separate here. Now here's the thing. P can either be true or false, right? And it's also true that Q can be true or false, but what happens, because we're using two variables, that means we're actually going to need 4 lines, okay? So we'll put true, true, false here. Well, you know what, let me go back here. There we go. Because the reason here is in propositional logic, we always start with the P. Generally speaking, we say that we're going to write word true, true, false, false, and then true, false, true, false. Okay, so what this means is that if these are all the possibilities for these. Now remember here, you can just use basic mathematics. If there's 2 possibilities for truth possibilities, either true or false for any one proposition, and we have 2 variables, then that means 2 times 2 is 4, which means we're going to have 4 different possibilities. Either both P and Q are true, or P is true and Q is false, or P is false and Q is true, or they're both false. Those are all the possibilities in terms of P and Q. Now, what happens if we conjoin them? Remember, conjunction means we're basically saying that P and Q, okay? So we're going to write it like this, P and Q. So what are let me change the color here. What are the truth function now? What's the truth properties here, and what's the truth functionality? Well, think about it here. If I say that Joey is going to the market and he's going to buy bread, right? Under what conditions would that conjunction be true? Well, if Joey was actually going to go to the market and it's also true that Joey was buying bread, then the statement Joey is going to the market and he's going to buy bread would be true, right? But what if I said Joey's going to the market and he's going to buy bread, but it turned out that he went to the market, but it wasn't true that he was going to buy bread? Would this original statement be true? The answer is the conditional here would be false, right? Because if I say Joey's going to the market and he's going to buy bread, in order for that full compound statement to be true, both sides, the P and the Q here, have to both be true. So what it means here is that, it means that actually all of these are going to be false down here, right? Because if I say Joey's going to the market and he's going to buy bread, but he's only buying bread, but he's going somewhere else, then that statement was false. And of course, if he doesn't go to the market and he doesn't buy bread, then it's false too. So what's the rule here with conjunction? Is that it's only truth functional when both variables are true. Right? Or you might even say it like this. In order for the conjunction to actually be truth functional, both variables must be true. Any falsehood means it's false, and we can write that down here too. Any falsehood and the conjunction is false, right? And you'll see here that conjunction is the strictest. Conjunction is the strictest of all the truth function. It's the strictest logical operator in terms of truth functionality. Okay, so let's just go through here. So what's the next one? Let's look at disjunction, right? If we have disjunction. Now remember, disjunction is that lowercase v, and it's basically when you have, it basically means or. Okay, so let's write it out here. We're going to basically create our table again. PQ, and then what happens if we have P or Q, right? Well, here we're just going to list out the possibilities. And in the next video, I'm going to give you the formula here for always knowing how long a truth table needs to be. At this point, you don't really need to know it. I'm just hoping that this will help you understand how we can determine the truth functionality of these propositions. Okay, so let's give an example statement. Let's make a disjunction. Either you're going to the carnival or you're going home, right? Or Joey's either going to the carnival or he's going home. So under what cases would that be true? Now remember, we mentioned that we use an inclusive disjunction. Let me erase that. And remember, this is important because the inclusive disjunction means either one is true, either one of them is true, or they could both be true. Okay, so let's take a look at it. What if I said, what was my example here? If either Joey's going to the carnival or Joey's going home, right? Well, let's imagine here. What if it's true? Remember, since we're using the inclusive disjunction, it could be the case that Joey's going home after he goes to the carnival, right? So it's true that he's going to go home, and it's true that he's going to go to the carnival. In this case, the disjunction would be true, right? The disjunction would be true. But let's ask this. What if Joey, if I go back to it, either Joey's going to the carnival or he's going home. What if Joey just goes to the carnival, but he doesn't go home? Well, this statement would actually be true still, right? Because that's what or means, really. But what if he goes home instead of going to the carnival? Well, this statement is still true, right? But what if Joey doesn't go home and he doesn't go to the carnival? What should we say? Well, this statement here, right, would end up being false, right? And what it means here is to have a disjunction means that it's always true unless both variables end up being false. And that's going to be sort of the basic rule you need to know, right? Whereas conjunction was the strictest, disjunction is the loosest in terms of its truth functionality, right? So just think like this. A disjunction is always true unless both variables are false. Okay? It's always true unless both variables are false. If both variables are false, then it ends up being false, okay? So that's the truth functional definition for disjunction. So let's move here. We have two more to go, the conditional and the biconditional. The conditional is actually going to be the hardest one for most people, I think. And remember, we're using this sort of horseshoe looking thing, and this basically means it's a conditional, which basically means an if then sort of statement. Okay, so let's sort of see if we can write the definition for this. We have P and Q, right? And this is going to be if P, then Q. Okay, so that's true, true, false, false. And then that's true, false, true, false. Okay? Now let's give a statement. In this case, let's give a statement. If you do your homework, then if you get an A on the test, then you'll pass the course. Let's imagine that's our example here. You'll see this is an important example, right? If you do your homework, then you'll pass the course. Right? Okay. So let's imagine. So that would mean that our P, right, doing your homework, right, this actually is where our P is. And then passing the course, this ends up being our Q. Okay? So under what conditions would the conditional statement be true, right? Well, think about it. If I said, if you do your homework, then you'll pass the course, and you did do your homework, and then you did pass the course, then that would mean that this statement that I told you was actually a true statement for you, right? It was a true statement. Now, what happens if you do your homework, and then I fail you? You don't pass the course. Well, ask yourself, in what way, under what circumstances would you consider me to be a liar, right? If you did your homework and then you didn't pass the course, well, that would mean that this statement was false originally, right? It was a lie, because what does the conditional mean? The conditional means that the consequent should follow the antecedent, right? And if that doesn't happen, then the conditional statement was a false condition, right? So let's go back to these. What about this? What if I say the statement, if you do your homework, then you'll pass the course? What if you don't do your homework, but you do pass the course? Does that mean that this statement was a lie, right? Well, not necessarily. If you don't, because this statement never said if you don't do your homework, then you won't pass the course. It only says if you do your homework, then you will pass the course. And this is an important point that's worth taking a moment to talk about, is that it's very, very important in logic that when we read a proposition or a statement like this, that we only analyze it according to what is said, that we don't infer anything past that, right? Most of us would just sort of quickly read this and say, well, that means if you don't do your homework, you're going to fail the class. But that's not exactly what this says, right? There may be other ways to pass the course as regards this example. So let's go back over here. What if it's false that you didn't do your homework, but you did pass the course? Was this statement a lie? No, this statement was still true, right? At least it still could have been true. So we can say that it's still truth functional, even if this is false and this is true. Well, let me give you another example. What if you don't do your homework and then you don't pass the course? Was this statement false? Right? This statement was, if you do your homework, then you'll pass the course. Well, if you did neither, you didn't pass the course, you didn't do your homework, this statement was still actually true, right? And so this is the bivalent sort of definition for the logical operator of the conditional, which basically boils down to this principle. It's always true unless the antecedent is true and the consequent is false, right? So conditionals are always true unless I'll just put A here for the antecedent, is true, right? And the consequent, I'll just put a C here, the consequent is false, right? And that's the basic definition you need to remember here, is that essentially whenever a conditional statement is given, it's always truth functional unless it breaks the very definition for what a conditional, meaning the consequent doesn't actually follow as a consequence, right? So that's the definition for the conditional. All right, let's scroll down here and let's do our next one, our last one. This is the biconditional. Remember, for the biconditional, we're using the symbol of a triple bar, and the biconditional means if and only if, right? If and only if. Okay, now let's do our P and our Q here. We have P if and only if Q. Now the P, we just write it out here, the true, true, false, false, true, false, true, false. And let me say, while you're watching this video, if you're sort of having trouble keeping up what I'm doing, feel free to pause it, think about it, read your book, and then come back, right? This stuff isn't easy initially to get, but you'll see that once it clicks, it actually isn't too difficult. But at first, it can be sort of tricky, okay? So let's, and I think this is sort of helpful to ask yourself, under what cases would it be like? So let's give an example here. You'll pass the course if and only if you do your homework. You'll pass the course if and only if you do your homework, okay? So the first one here, right, you'll pass the course. This would be our P. Whoops. All right, this is our P. And then this here, if and only if you do your homework, this is our Q, okay? So, under what cases would this be a lie? Well, let's think about it here. If you pass the, if I give you the statement, you'll pass the course if and only if you do your homework. You do pass the course, and you do your homework. Was this original statement true? The answer is yes, it was. I wasn't lying to you. I was telling you the truth, right? But let's imagine, what if I say you'll pass the course if and only if you do your homework? You end up passing the course, but you didn't do your homework. That would mean this statement was what? It was false, right? And then what about here? What if you don't pass the course, but you did do your homework? Was this statement true or false originally? You would say I lied to you, right? So that would mean that it's false, right? And then finally, what if I said you'll pass the course if and only if you do your homework? You don't pass the course and you don't do your homework. Well, that's what you expected would happen. That's what if and only if means here. So we would say that's true, okay? So that means that the truth functionality of a biconditional is dependent upon each variable having the same value, either truthhood or falsehood. When they get mixed, that's when they're false, okay? So let's maybe write that out, since we've been writing out these sorts of, these definitions I'm writing out here aren't the sort of strict definitions that a logician would like. For instance, any logicians watching this will be unsatisfied. But we're not making these videos for logicians, we're making these videos for students, right? So it would mean this. In order for a biconditional to be true, both sides, right? Both sides, or both variables, must have the same truth value. Okay? So in order for a biconditional to be true, both sides or variables must have the same truth value, otherwise they're false. Otherwise the biconditional statement is going to be false, okay? So let's sort of do a real quick overview again. Gee, my handwriting looks bad, so I apologize. It looks like a third grader wrote this. Okay, so we have negation, right, which is easy. Basically, a negation means that you have the opposite truth value under the negation. For the conjunction, when both variables are true, the conjunction is true. Otherwise, it's false. Right? Any falsehood in the conjunction ends up being false. If we look at the disjunction, right, then what we have here is the rule that, right, that the disjunction is always true unless both variables are false. For the conditional is always true unless the antecedent is false while the antecedent is true while the consequent is false. Otherwise, it always works, right? And then finally, the biconditional is one, they basically have to have the same truth value to be true. Otherwise, they're false. You can't mix up the truth values for the biconditional. So let's sort of draw out here the final sort of phrase of doing this, right? And this is what you really need, P and Q. This is what you should really write out in terms of your homework. This is what you really need. So I would write, if I were you, I would write this down. And in fact, your book has this on the very last page, or if you're using the online version, you can actually pull it out yourself. So here are the different things. We have negation, conjunction, disjunction, conditional, and the biconditional. So this is what it's going to look like. Well, the disjunction is sort of difficult here. Either it's going to be true, or it's going to be, I'm sorry, if you negate, right, because the disjunction only refers to the P here. So if this is true, then the negation's false. If it's false, then it's going to be true. Those are the only possibilities for the negation. But for the conjunction, it's going to go true, false, false, false. I don't know why. This Microsoft Word is not working well today. Okay. Okay. For the disjunction, right, it's always true, right, unless they're both false. And for the conditional, it's always true unless you have this from true to falsehood. True and true. And then this is going to be true, false, false, and true. Okay? You know, in fact, this is probably just confusing to put the negation here at all, because the negation only uses this, so let's just do the negation separately. True and false. And if you negate it, you're going to put false and true. Okay, negation is really simple. What you're really going to have to focus on is these guys, right? The conjunction, the disjunction, the conditional, and the biconditional. And basically, there's no easy way to say this. You're just going to have to memorize this. The good news, though, is that as you do the homework problems, you're going to see that you're just going to memorize it, okay? Now, why does all of this matter? The answer is because what we're going to show you how to do is using these definitions, we're going to show you how to compute truth values. Okay, so let me give you just a couple examples here. Let's imagine, for instance, and this is where, remember, a critical concept here is the main operator. And I covered that in our last lesson, or I call this the main or the top level operator. Okay, so let's give this example here of A or D, therefore E. Okay, so this is our example here, and let's say we actually know that A is actually true, and we know that D is actually false, and we know that E is actually true, right? Let's say that we actually know that whatever this is, A stands for it's true, whatever D stands for it's false, and whatever E stands for is true. So how do we compute these, right? Well, what we would do is we'd say, well, if this is true and D is false, what is that? What did the rule for the disjunction say? Right? The rule for the disjunction said that the only way a disjunction can be false is if they're both false, which means that this must be what? It must be true. Okay? Now, E is true. Now, here's where it's going to get a little tricky. Ask yourself, what's the main operator? The main operator is this guy right here. It's the conditional. Now, what I'm going to do is, because remember, in order for the conditional to work, I have to compare this with what? Well, I have to compare it with the logical operator, the truth value that falls into the logical operator. So what I'm going to do is I'm going to compare these two things together using that conditional rule. Right? What was the conditional rule? The conditional rule says that if the antecedent is true and the consequent is true, then this is true. And then we'll circle it, because what it means is that this phrase here, given those particular facts, right, means that this statement is actually truth functional. It actually ends up being true. Okay, I hope that makes somewhat sense here. Let's give another example here, because what your homework's going to ask you to do is your homework's going to give you, it's going to tell you what the variables are, and then it's going to say calculate the ultimate truth functionality. You always want to end with the main operator, right? So it's sort of like math, right? Start with the premises, start with the parentheses, I'm sorry, and end with the main operator. Okay, so let's show you here the textbook. Whoops. Okay, and oh yeah, I could see here. Here's the definition for a truth function, right? A truth function is any compound proposition whose truth value is completely determined by the truth values of its components, right? And there are some statements in ordinary language that are not truth functional at all. But okay, let's sort of scroll down here. You can see here's all the definitions I just gave, and by the way, they look much nicer, right? Right? Negation, conjunction, disjunction, the conditional, or the material implication, as it's also known, the biconditional, or the material equivalence, right? See, they have to be the same. So let's scroll down here, right? And let's say onto computing truth values. You can see what they do here is they basically say, they sort of, in order to explain this, right, if A is true and D is false, then that means that the disjunctions end up being true. If E is false, right, then this ends up being false. You can see Hurley here gave different truth values for these things, so he ended up with the false one, while we ended up with the truth one, but that's simply because we said that A and D had different truth values, okay? But here's an example. Remember, they're always going to move from wherever the parentheses are and then move to the, ultimately to the last, to the final, the top level logical operator, to the main operator. Okay, so let's give a couple examples here. Even though this one's done for you right now, I want to show you how to do this one right here. Whoops, that's not the right thing. Snipping tool. Here we go. So let's do this. Okay, so let's do this problem here. And here, remember, what we're going to see here is we're going to say that A, and here I'm just giving you an example here. We'll say that A is going to be true, C is going to be false, and B is false. So let's assume that this is what is in fact the case. Whatever A stands for, it's actually a true statement, and so on and so forth. How do we do these? Remember, start with inside the parentheses, right? And just start by labeling what these things are, right? The C here is false, and the A is true. Now, what do you do here? Because the disjunction only refers to the A, we're going to say that this means this is false, okay? Now, what do you compare this C with? These, you compare it not, right? When you say the C or A, not A, you need to use the disjunction rule with this negation, not with this original A, right? So that means a false and a false disjunction is actually false, right? Now, let's go over here. The B, we said, was false. If B is false, then, and you negate B, that means it's true. Oh, wait a second. Which one do we do? What is the main operator? So you can see this is why it's important. Is the main operator the negation or is it the conditional? Well, the negation only actually has to do with this right here, this statement. So that means that the main operator is actually this conditional, okay? So if this is false and we negate it, then that means it ends up being true, right? And if we're going to compare truth and truth using the conditional rule, what's the answer? Remember, what was the rule we said? A conditional only is false when the antecedent is true and the consequent is false. In this case, the antecedent is true and the consequent is true, which means that this statement ends up being true. Okay? I feel like my chicken scratch isn't really probably very clarifying, so I apologize. But you can see here, I'm not sure what their truth values were here. Oh, they had different truth values, but ultimately they ended up with it being true as well. Okay, so let's do another one that's longer here. Let's snipping tool. You know what, let's do this in Microsoft Word instead. Okay, so let's take a look at this one. Now here we're going to assume that D. Let's assume that A, B, and C. Let's assume that A, B, and C are all true, and let's assume that D and F are false. Okay, so what are the basic steps? The first thing I would do, just to make it easy, probably, let's sort of write these down, is probably just place the truth value below each variable. Okay, so what do we say? We said that D is false, and we said that F is false. We said that B is true. We said that A is true. We said that F is false, and we said that C is true. Okay. Now you can see here, I always say start, just like in mathematics, start with the innermost parentheses. We have brackets here. And the truth is, you just have to, the rule is really you just have to always end with the main operator, but we'll start over here, right? And where should we start? Let's just start on this guy right here, right? What's the rule for the disjunction? If, let me change the color here, right? The disjunction rule was that what happens if D or F, both D is false and F is false, right? And you may want to do this problem on your own as I'm doing this and pausing the video to see if you understand this, okay? The rule was that at least one of them has to be true. So that means that this is going to be false, right? Now remember, so the negation applies to simply what follows immediately after in the parentheses. So if this is false and we negate it, what happens? What's the rule? Opposite truth value. So this ends up being true. Okay. Now we have a conjunction here, but we have to figure out what these parentheses are first, right? And of course, always start with the negation. So if this is true, this ends up being what? The opposite value. This ends up being false. Now we have to compare the T here with the F using the disjunction rule. The disjunction rule says if one is true, then it ends up being true. Okay? So now let's just sort of, that means we're going to be comparing this T and this T using the conjunction rule. What was the conjunction rule? They have to both be true. So this is actually true. Of course, assuming these definitions, because if we change these definitions, this would end up being different. All right, now let's figure out the other side, because remember, the main operator is this guy. And probably an important thing here is to, let me go, place the truth value. Let's put, determine the main operator. And 3, work out the truth values, beginning with the innermost, beginning with the inner, let's see, here we go. Okay, so I think the steps here is place the truth values below each variable, and then determine the main operator. And then once you determine the main operator, work out the truth values beginning with the innermost embedded statement using those operator definitions we did earlier. Okay, so let's finish this problem up here. Now, if C is true and we negate it, then it's going to be false, right? And what happens if we have now we have to use the conditional and compare this F with this F using the conditional rule. That means it's actually true, right? So now we've done that, and the negation applies here. So that means this ends up being false, right? And so here, I'll just really write down here. Because now what we're going to do is we're going to compare this one and this one using the main operator rule. But remember what we said? The main operator rule says that if the antecedent is true and the consequent is false, then this thing ends up being false. And that's the final answer here, is that this whole statement is not truth functional. It actually ends up being a false statement. Okay? So let's do another problem here. You can see here it's actually not too difficult, but you're gonna have to work slowly in order to see, in order to really get how to do these things. No, okay. All right, so let's do another problem here. You can see here this is what they ended up. I don't remember what they decided the truth values were. This one looks really ugly, so let's do this one so that way you can see what a really long, yucky, ugly problem looks like. Okay. Okay, let's just do number 2 here. Okay. Okay, edit, copy. You know what I'm gonna do here? Let me just open up a new file. Okay. Okay, so here's this statement. Ugh. What am I supposed to do here? Now, in this section, your homework is always going to tell you what the definitions for these things are. So what it's basically going to say is that A, B, and C are always going to be true. And D, E, and F, this one doesn't have a F on it, but D, E, and F we're going to say are going to be false. Okay, so let's just follow those steps out. Remember we said the first thing to do is just place what you know the values are underneath each of these. So that means C is true, E is false, A is true, B is true, B is true, D is false, C is true, and E is false. Okay, so now let's work it out. Now you can see here the first thing I need to figure out is what the heck is the main operator, right? And I'm going to highlight the main operator. You might think at first that this is the main operator, but wait a second. Notice we have parentheses, we have brackets, and then we have the squiggles. So that means that this right here, the negation is the main operator. This is where I want to end up. So just like in mathematics, I want to start with the innermost parentheses. Okay, so let's use green here for our colors. And always start with negation. So if this is false, then this must be true. And what's the rule for the conjunction? If they're both true. So this ends up being true. And I'll write it down here. Okay, so let's go over here to the next parentheses within this bracket. Let's look at the next parentheses, right? If B is true, then what's the negation? Right, it's false. What about the conjunction? If this is true and this is false, what about this conjunction? That means this conjunction is actually false. Because remember, the conjunction rule is the strictest rule. It means that we absolutely have to have both sides of the equation be true. So then let's go back here. Let's finish off what's inside these braces here, right? So let's just, here, maybe this will help. We're going to finish this thing first. Okay. So let's go back to our green. So if this is false and we negate it, what does that mean? It means it's true, right? So if we use the conditional rule next and we say true to true means what? It means true. Okay, so that means we've done that. So let's go over here. You can see here that the next brackets is what I've got to do next. Okay, so B or D, one of them has to be true, and it is, so that's true. And then negation, so that means this is ended up being false, right? Because when you negate this, truth turns to falsehood. Now let's go over here. Now this is tricky, right? We haven't seen this kind of problem yet. I don't want to start here. I always want to start with the negation. So this truth becomes falsehood. And then I'm going to compare this one and this one. I'm going to compare these two guys together, right? So that means a false and a false on a disjunction is what? It's false according to the rule. One of them has to be true. Now, here's where I go to the next one. I'm comparing this one here. And I'm going to be looking at, here's the little operator that sort of governs what's in the braces here. So, a biconditional, what was the rule? The biconditional is that both have to have the same truth value. So that means we're going to compare this one and this one. And they do using this rule, which means that this ends up being true. Okay? Now, we've got to look here. at this conditional. Okay. So the conditional rule says that it's true unless it's true and then false. So that means that when I compare these two things together, this is true. Now I can go to the main operator, which is the very end. Now, if this is true and I negate it, then that means that this was false. Okay, so now you can see I'm able to actually compute very complicated statements in propositional logic using these rules. The trick here is to be deliberate and slow and try to be very, very clear. I actually encourage you, especially if you're handwriting these, to use graph paper instead of a blank piece of paper or something like this. Use graph paper because those lines will help you keep everything straight. And I actually encourage people to use highlighters and stuff like this and multiple pens. At least when you're starting, just learning to do these propositional problems, it's helpful to use the different colors because then you can see what you're comparing, and also to go level by level. And that's essentially what Hurley does in the textbook as well, right? You can see, well, he doesn't do it here, but this is what he does in multiple points. Okay, I'm going to sort of skip this section now, which is sort of on some of the important elements on how to translate these propositions. You should really read them, but it's not as pivotal in terms of what I find that most people really need to be thinking about. So what do you have to do in the exercises, right? The first thing you have to do is identify the main operator, right? They want to get you to learn to see that main operator, because if you don't see it, you're not going to do well. So what is the main operator in this first one? It is the conjunction. It's the conjunction. Okay, I'll just jump to here. What's the main operator here? Well, because I have these braces, that means the negation is the main operator, right? Now you can see here, what they're going to next give you here are compound statements in normal language that are historical, so you know what they are, and then you're going to use your knowledge of historical events to then determine what the definitions for each variable are, and then ultimately to identify the truth value. So let me give you an example here. Let's do one, just so you can see how to do it. Let's do number 2. Okay. Nixon resigned the presidency and Lincoln wrote the Gettysburg Address. The first thing we got to translate this is Lincoln resigned the presidency. So let's just put N, right? And Lincoln wrote the Gettysburg Address. We'll put that as an L. And then we have an and. So that means we have a conjunction. So we have N and L. Now, Nixon resigned the presidency. That is true. And Lincoln wrote the Gettysburg Address. That is true. So what's the truth value here? Well, the conjunction here means that this is true. Okay? So that's essentially how you do these problems here. Maybe we should do one more here. Maybe one that's a little tougher here. Okay. Lincoln wrote the Gettysburg Address if and only if France bombed Pearl Harbor. Okay, so that's L, if and only if. And remember, France bombed the Pearl Harbor is going to be the proposition, so we'll just put F. Now, it is true that Lincoln wrote the Gettysburg Address, but did France bomb Pearl Harbor? No, that's false, which means in the biconditional rule, right, they both have to be the same truth value. They're not, which means that this is false. Okay? It's actually not too difficult, but then again, I've done these many, many times. So just work slowly. I mean, obviously they get complicated here when you get Custer was killed by the Indians and all these sorts of things. And if for some reason your knowledge of, because most of these are American history, if your knowledge of American history is poor, just use Wikipedia to figure out what was true. Okay, now you can see here what we were doing just previously, the problems. This is what the third section is going to ask you to do. It's going to determine the truth values by the following simplified statements. Let A, B, and C be true, X, Y, and Z be false. Circle your final answer, right? So I'm going to do 2 of these problems and then I'm going to end the video here. So let's just do number 3. Okay. If X, remember X is false and Y is false. So the next thing to do is to negate it. So if the negation of a falsehood is going to mean this is true, right? If this is true, then that means I'm going to compare this one and this one together using this rule, the disjunction rule. The disjunction rule says that one of them has to be true, and look, one of them is true, so that means that this is true. That's how you do those problems. Hopefully your handwriting is better than mine. Okay, let me do one last problem. Well, let's do a complicated problem. So that way you can see that you can do complicated problems. It's actually, all you have to do here is for the complicated problems is just move slowly and deliberately. Remember, first put down all of the variables values that you have, and then from there, simply move, figure out what the main operator is, and once you figure out the main operator, you know what, here, let me copy this. I think it's easier to use in Word. Okay. Okay. So, once again, here, let me repeat myself. Put in the truth values that you know. So let's start with that step. Right? In this case, this is false, false, true, false, true, and true. Now, figure out the main operator is. What is it? Remember, that's why it's so important to have the braces. That's the braces there. So that means that this is the main operator. So let's put an arrow. This is the main operator. Now that I know the main operator, I need to start with the parentheses and work my way out. And you can start on either side. We'll just start with this side since it looks easier, right? The conditional, we're using the conditional rule, looking at falsehood and falsehood. That's actually true, even though it's counterintuitive. Let's go over here. Let's start with this one over here. If this is true, that means this is false. And true and false, disjunction, that's true. And then I have to negate it. So that means it ends up being false. Okay, let's move over to this side. This is sort of the main operator for this little section here. So if this is false, this ends up being true. The biconditional rule says they both have to have the same value. It does. So now I'm going to compare these two, this one and this one, using this rule, the conjunction rule. The conjunction rule says they both have to be true, so that means it's false. Okay, it may be helpful here to underline it. So that means I'm going to compare this one and this one using the real main operator, the conditional. Truthhood to falsehood under the conditional means that this is false. And you circle that, okay? And that's basically how you do these problems. It really isn't difficult as long as you're just slow and deliberate, okay? That's section 6.2, truth functions. Thank you guys for watching and having patience with all of my my handwriting issues on this video. So it's good working with you guys. In our next video here, 6.3, we're going to be looking at actually what happens if you have a proposition but you don't know the truth values. How do you begin to determine whether or not an argument is going to be true or not? So we're going to introduce you to using truth tables in a much larger sense. So that's what we're looking at in the next video, okay? Thank you very much for watching. I'll see you guys later.